Uh, Thank you, Neelima, and good morning once again to all of you. I would like to thank organizers of this meeting, Climate Dynamics and Network, Neelima, Ram, and Rupali, for giving me this opportunity to discuss about the work which we are doing at our lab at Central City of Rajasthan. And it is mostly related to the reservoir computing aspect, which is a relatively new phenomena or new dimension in the machine learning framework. And since we are here for climate dynamics, so I will give you these two talks related to the learning dynamics. Today we will have a brief introduction of the dynamical system and reservoir computing with one example of learning dynamics of the chaotic system, which is one of the early model proposed by Lawrence while he was working on the climate model itself. And tomorrow we will have the in the second part I will discuss about the multi-stable system dynamics prediction, where we have a more than one attractor coexisting at the same parameter depending upon the initial conditions. And we will also look at the multi-parameter dynamic prediction, when the more than one parameters can change while you are on the way to the system. So I would like to thank my collaborators, Avdesh, Manish, Martin, Nikoli, Sudeshna, Sarnendu, and Swati from different places, those who are working as an external collaborator or my students at the lab. And I would also like to thank DST and SERB for funding me on two different projects related to the reservoir computing and attractors. So as I told you that today in the first part of my talk, I will give you the brief introduction of machine learning and dynamical systems before we move to the reservoir computing, which is the main concept I will be delivering today. And then we will discuss about the one example of learning dynamics with a single node reservoir, and then we'll conclude the today's talk. So as we all know that in the traditional programming concept, we give the input data and set of rules to the system and we get the output. While in the machine learning framework, we give the data and output also as the input data to train the machine to find out the set of rules. Once we have identified the rules, then we can use this machine for further prediction of the system dynamics. And broadly, we classify them into the supervised, unsupervised, and reinforcement learning framework. So I will not go into the detail of all this, but these are basically where the intervention is required or without any intervention, which is unsupervised, and we have the feedback loops in the third category. And since we will finally move to the reservoir computing, which is the deep learning framework, and this is the subset of the machine learning, and it uses the neural network architecture, where we all know that the initial neural network concept was built based on the human brain, inspired by that. And since there are certain limitations of the traditional neural network, where the deep learning neural network with the large number of hidden layers help us in the understanding of more complex systems. So this is the typical structure of the neural net, where you have a n number of input layers where you feed the input data, and then you have a large number of hidden layers where you do the data processing, and finally you get the output at the output layer. So in the traditional neural network framework, we do the data processing on the large number of hidden layers where the weights are optimized. And in this optimization process, it takes a lot of computational time. So one of the basic unit of this neural net, which is inspired by the human brain, is we can call it again the neuron, or the unit of the network, which get the input from all other neurons and the output is the weighted sum of the input from all other sides with some bias, and it is in the mathematical framework with some functional output, which can be any mathematical function. Mostly we do it with the sigmoid kind of functions, which classify the output into the um, two different class or the binary form. So if you look at the typical training, the procedure of any the neural network is that you give the input to the input layer, and then you do the data processing, where the input which was initially given to the input layer, it processed through the weighted sum from all the neurons in the network of n cross n nodes network. And then what we do is, whatever output we get, we compare the output with the target value, because in the training time the output is given to us, and whatever output we receive from the network, we compare it with the target value, and we calculate the loss function. So what we do is, the weights, which are the connection weights in the networks, are optimized in order to reduce this loss function. So once we get the optimal value of this weights by optimization procedure, then we set the weights, and then we don't need any further training. And based on this weighted network, which is a fixed weight now after training, is used for the prediction purpose. Yeah.
Layers, right?
Yes.
And some matrix which is linearly connecting the output to the
Correct. Yes.
So, like, so any nonlinear system can be written in this way, and just because it's very nonlinear, you need more layers. Like, how do you decide the number of layers or something?
Yeah. So the decision of the number of layers will depend upon your exact problem. Like how many, I can tell this in terms of, like, if you want to classify the two different objects, say A and B. Okay, so for that you may not need large number of hidden layers, because these the classification can be thought of a kind of two different attractors in the state space there of the neural net. Or, so I will come to the dynamical system later on. Those who have already studied the dynamical system is like, so here what is happening is, you have the any given node get the weighted sum from all the neighboring nodes, and there is a weight matrix which is a n cross n matrix. Okay, and then you have some function which you can think of any nonlinear mathematical function. Now what is happening is, when you have say for example only one layer with only two neurons, or maybe large number of neurons, then this when you evolve this with some kind of, it is a kind of the kind of map, okay, so which is taking you to from one state to the another state of the neuron. And in this process, basically you are this is the dynamical system which is evolving in time, this neuron, and it is reaching to the some state which is a kind of asymptotic state, or the attractor of that neuron, or final state of the neuron. Okay, so now if you want to classify only two objects, okay, so you need basically two attractors. So these two attractors can be planned in the small network, or these two neuron model system can share the one state for the one output, or another state for the another output. So depending upon your complexity of the problem, you need large number of hidden layers. So when you increase the large number of hidden layers, so that means you have a, like for example, if you have a n nodes with n layers, you have a n square nodes. These n square nodes are, and each node has a one state variable. For example, so your state space is n square dimension state space. So in the n square dimension state space, you can define or you can classify large number of energy states which are completely different, and that can be used for the classification purpose. So number of hidden layers will actually depend upon the complexity of the problem. You may not need large number of hidden layers. So that's why this deep learning concept came later on, when people were not able to work with the traditional neural network.
Manish,
Yes.
does the number of neurons you need, is it dynamically adjusted, or is it fixed and then you do a calculation, then you increase and then you do another calculation?
So typically it is fixed. So number of nodes are fixed and weights are also fixed. So it is a static network, not a dynamical network.
I mean, could one incorporate an evolving network?
Yes.
That
Yes.
shows something that the problem is so difficult that it needs more and more and more brain power.
Correct. So yeah, you're right. So recently there is one study where one group of people have tried they started with the less number of nodes, and slowly they were adding more and more nodes, and also they have worked on the different kind of network topology, or the dynamic network, where you can have a new nodes added to the network, and also the connections can be dynamic. So it is a
Sparser.
yes. Yeah. Yes.
See, suppose I use the number of hidden layers.
So
Like I could still have lots of zeros or near zeros in that bit.
yes.
So I may actually be able to deal with the sparser bit.
Yes. Yeah, that can be done. Yes.
Do you actually ever look at the weight matrix?
That is random, but there are certain studies where people have studied the network topology. So you can also have an optimal network. So there are certain studies.
So, expanding on this idea that, how does one decide whether you need more or fewer nodes? I mean, it will depend to some extent on what the weights are.
Yes.
If some weight is 10 to the 6 and the other weight is 1,
Yes.
then perhaps you don't need the 1 and you need only the 10 to the 6.
Yes.
So that's, I think, what.
Yeah, and in the concept of the reservoir computing, exactly that was the idea, that they have fixed the weight. Because when the initial or previous neural network architecture, people were optimizing all the weights. Instead of optimizing all the weights, they tried to fix the random weights, and that was also working well. So it is not necessary to optimize all the weight all the time. So those who are familiar with the field, but it's okay. But otherwise, please feel free to ask me if you have any basic understanding issues, because what I am talking right now is about the very typical structure of neural net, where X is your input, and then you at any node you get this weighted sum, and this you can have a bias, and then you have some you can take the 10 hyperbolic function of this weighted sum, and that will be your output. And during the training part, you know the output, so this function is equal to the output, and then you compare the difference, and you change the weight to minimize this difference, and once it is minimized, then you fix the weight, and then you know the input and weight, so you can calculate the find out the output, which is the kind of prediction there. And one method is the gradient descent method, which is again this energy minimization method, where the weights are updated by in this fashion, where the new weight is previous weight minus lambda times the gradient of the f. F is your loss function, and lambda is some rate of descent, which is the constant, which also it is a hyperparameter which you have to tune while doing this calculation. So this is a very standard procedure of the machine learning. And let's quickly talk about the dynamical system. So what is the dynamical system? Any system which is evolving with time is called the dynamical system, and we can classify them into the linear and nonlinear dynamical system depending upon the function, whether it is a linear function or nonlinear function. Or if your time is continuous or discrete, you can put them in the class of flows or maps. Okay. And if you just recall what I have told you in the neural net architecture, we are basically using the map, and you will have a next talk on the maps itself. So you can see that if any state of x is given to you initially and a is given to you, you can find out all the iterative states of this map, which is the kind of dynamical system. Yeah.
Not a dynamical system, like if it has a memory, then like can you use these approaches? Like I'm saying x of n plus 1 is not just a function of xn, but it's a function of all the prior x's. It has a memory.
Yes. So yes. Delay systems, time delay systems. Yes.
You can use the same approach.
Yes, same approach. It is the system has only the memory of previous state, but in general you can have a memory up to the last kth states, and it will work there also. And there you can put in the continuous system, you can put the time delay tau, or here also you can have a like the memory up to the kth steps, like that. So
right-hand side, if you have a previous time, right? Then you need to know all the previous times up to the present. So it's like infinite.
Yeah, but suppose it explicitly depended on all.
It depends on what the function is.
Yeah, maybe we'll talk later.
yeah. So all these systems, if you look at if you solve this the differential equation or difference equation, you will get the time series in time for the x, and you can see that after a certain time, if you remove the transient time, initial time period, the system will try to settle down to a certain state, and this we call it the attractor of the system. And the initial condition which is going to this attractor is called the basin of attractor. So set of initial conditions. So you identify all the initial conditions which are going to the attractor is called the basin of that attractor. And then what can happen is the one system can have one attractor for a given parameter, or it can have a multiple attractor, like you can have a double well potential or another this kind of problems. Or when you change your parameter, you can go from one attractor to another attractor. So what I will tell you about that, that these attractors can be classified as a point attractor, which we are going to the fixed point, so there is no more dynamics there. Or it can be a periodic attractor where you have a certain, after certain time, your motion is repeated. And one of the example is the limit cycle. You can have a quasi-periodic attractor. You can also have a chaotic attractor, which is the bounded trajectory, but with the unpredictability in the motion. That means that you have a sensitivity dependence to initial condition, that two nearby trajectory, even though they are starting from very close initial conditions, they with time they diverge in space, however still maintaining the same subspace for the bounded attractor motion. We can also have a strange non-chaotic attractors which are having a strange geometry, but they are not call it the chaotic attractors because of their negative Lyapunov exponent or the non-chaotic motion, which occurs mostly in the quasi-periodically forced systems. The another class of attractor is the hidden attractors, which we call the hidden because it is very difficult to localize them or identify them because of the tiny basin of attraction, and they generally have in the system where there is no equilibrium point. So most of the dynamical system, if you solve the differential equation or difference equation, you will always get the equilibrium point. But in certain systems, you don't have any equilibrium point, and still there is the state of attraction, which is difficult to locate in the absence of the equilibrium point. So one of the important the dynamics is the chaotic dynamics, and this was like one of the model was proposed by Lorentz while he was simulating the fluid convection, and you can see that these two trajectories will start in a very close vicinity. With time they diverge, however they are maintaining the same attractor dynamics. Okay, and the divergence from the nearby trajectory is measured in terms of Lyapunov X point. And this is the model equations where X is the rate of convection and Y and Z are the horizontal and vertical temperature variation, and they are rho, sigma and beta are the parameters. So what we will do is, if you look at the dynamical system, whatever I told you till now is that any dynamical system will asymptotically reach to a state of attraction, which we call the attractor. And all set of initial conditions which are going to that attractor is called the basin of attraction. And for a given parameter setting, like for example, if you set these system parameters, you get one particular type of attractor is called the attractor of the system for a given parameter, but there is a possibility that you can have a more than one attractor at a given parameter value. We call it the multi-stable system. Another thing what is there is that if there is a single attractor or multiple attractor, if you change the internal parameter of the system can show a phase transition from one state to the another state. Okay, so if you look at the climate systems, if they put them into the class of the dynamical system, you can see that they show this kind of chaotic behavior, which is long-term periodic behavior and which is very sensitive to the initial condition. They also show the complexity in terms of multiple coexisting attractor at the same parameter value. And when you change the parameter, they also show the phase transition from one state to another state. So I will not discuss about the climate models, but I will give you some flavor from the different model systems where we can learn the dynamics and do the prediction. My talk will be in two parts today. What we will do is from the reservoir computing, we will try to predict we will give the input X and try to predict the Y and Z variable using the reservoir computing concept. And in tomorrow's discussion, what we will do is we will look at the system which has a more than one coexisting attractor, and we train the system for one attractor and try to predict the unseen attractor. Okay. And in the third problem, tomorrow what we will do is we will discuss about the one problem where there is a sudden change in the parameter, or there can be a change in the two parameters simultaneously. So can we learn the dynamics of the system from a few initial settings and explore the entire parameter space, which we can call it the two parameter bifurcation or multi-parameter dynamics prediction. Okay. So let's first look at what is reservoir computing. So we have already seen the neural network architecture, and this reservoir computing is basically the deep learning framework where we use the recurrent neural network architecture. And what is the recurrent neural network architecture? Is basically it is a kind of network with a large number of neurons which are connected to each other, and there is a recurrence relation between them. Okay, and there we can put them into the three components, the neural net which we have seen. So first is the input layer, and hidden layer we can replace by the dynamical system. So what we are doing is the entire the neural net which is in the hidden layer is replaced by the dynamical system. It can be any dynamical system, any physical system, which is called the dynamical system. And then we have an output layer. So the input connections, the reservoir, the dynamical system, and then we have an output. So if you look at the origin, it was developed independently through two model systems, eco state network and the liquid state machine. So yes. Yes. Yes.
Connections are whatever is the hidden layer.
Yes.
How do they feed into the and
So yeah, so what we are doing is, you can think of any complex network, or it is a like this you can this hidden layer, you can think of a one oscillator, simple oscillator, or you can have a two oscillators or two dynamical systems which are connected with each other, and they have their own internal dynamics. Okay. And then input is fed to that. So if you look at the neural network framework, where we have seen that the weighted sum is given to the neuron, which is the output. So here also it is like instead of that 10 hyperbolic function, we can use another function, which is our the dynamical system governing equation. Okay. So I'll come to that later on. So if you look at that, you can see that it basically utilizes the rich dynamics of the dynamical system, which is able to multiplex the complex input. So what is happening is that you think of the dynamical system, one unit, or you can have a more than one unit which are connected in the network form, and the input is given to the network. So when you give the input to the network, so network has its own internal dynamics. So if I call the network dynamics node as a x and input is I, so I is added to x. So x plus I evolves with the internal dynamics of the system. So what is happening is the input information is added to the or stored on the top of the state of the reservoir, which is the dynamical system. So dynamical system is carrying your input information in time, and then you are extracting it at the end of the day. Okay. So what, as compared to the traditional neural network, what you do is you fix the input weight, you fix the reservoir weight, and you just allow the output weight to be trained, which is in the readout, and that can be done through the linear regression. So you simplify your problem from the optimization of n square weights to simply n weights, and this is only at the readout. So when you compartmentalize into the three components, okay, so it is very easy to go in the application side also. So you can have a reservoir which is trained, and then you can have a connection. It can be a two electronic circuits, one is connected to another one, or you can change it to the other one also. So that main body can be used for the multiple tasks also. That is fixed, not optimized. Yes, these are the hyper, yeah. So everything is fixed. When I'm saying fixed, there are certain limitations which I am not talking right now. They are called the hyperparameters. So you have to adjust the hyperparameters during the initial training part or the setting part. Once it is done, then your job is left only to optimize the output weight. So how it works? Okay. So if I look at the working principle of the reservoir is the input is encoded to the reservoir. Okay. So what I said is the input is I, that is added to the state of reservoir x. So it is x plus I, and then you have a function of x plus I. Then what you do is, because now the reservoir is a dynamical system, so it is keep on evolving. So you store all the states of the reservoir, and then you optimize the output weight at the output layer. Okay. So there are certain criteria for the reservoir. So it has to be a high dimensional, because you have to store large number of input to the reservoir. It has to have a rich nonlinear to to have a perform this information processing there. And then there is a fading memory which is associated with the basically you basically don't have any sensitivity with respect to initial conditions, because every dynamical system asymptotically reaches to an attractor. So you think of a large number of attractors in the space, and you are using the attractors as the learning space for the this machine. Okay, and we use generally the network of nodes, and we will use the eco state network, which is the random network. So what you can do is you can build a random network, okay, where this connection weights are randomly put. So and the nodes have internal dynamics. So here, when you are using the random networks, which is like you can use the Erode network also. So all the weights are fixed, but hyperparameter we will decide later on. So this is the one example of the eco state network. Okay, so you can see that this is the reservoir computing framework. U is your input, X is the state of the reservoir, and Y is output. During the training, Y is given to you, U is given to you, and X is updated by this equation, and it is a difference equation. Okay, so X is a minus 1 xt plus a 10 hyperbolic, the weighted input U t plus 1 plus the weighted sum from all the nodes in the reservoir. Xt is the state of the reservoir, and W is the weight matrix of the reservoir. And if there is any feedback from the output, that can be added here. If there is no feedback, we can remove this term. Then the relation between the Y matrix is W out times X matrix. During the training time, Y is given to you, so you can work out the W out through the linear regression. Once the W out is known, that can be fixed here, and then W out times X, the output of this equation, will be put here, and then you can get the Y, which is the prediction of the state. This is very simple structure, and one can write down the code and can do it. It is not a very difficult task. So now you can also have a physical dynamical system as a reservoir. Instead of a mathematical framework which is given in this eco state network, you can also have a physical reservoir which can be used. So what I'll do is I will give you some examples here, then we will come back to the eco state network, and we will use this equation for the reservoir computing. Okay, so now either we can have an eco state network, which is a random network in the mathematical framework, or we can have a physical reservoir, or we can use any other net reservoir also. So let's see that some of the examples I'm mentioning here is the electronic system reservoir. You can have a spintronic, you can have a mechanical system as a reservoir. So here these are the nodes, and they are connected in a particular fashion or random fashion. You can also have a DNA oscillator as a reservoir. Now, when you use a dynamical system as a reservoir, it can be a coupled oscillator. You can have a delay dynamical system as an oscillator, where the delay coordinates will work as a virtual nodes there. Okay. Now, quickly, I will tell you about the single node reservoir. Suppose this the reservoir, which is a collection of nodes, if I replace it by the single node, what will happen? Okay. So I have 5 minutes now. Correct. So maybe. Okay. So.
Infinity had 5 minutes.
Okay. So what we can do is, can we have we were having a discussion on the size of the network. Can we start with the single node and see whether single node reservoir will work? Okay. So there are certain examples. You can see that the chaotic LC delay feedback, quantum RC driven pendulum, and then in the neuron model was also used in the deep learning. So I will give you the example of single pendulum reservoir. Okay. So you can see that how this reservoir framework work here. with the single pendulum reservoir, and our task is, sorry, then I will stop. Yeah, tomorrow I will continue with the coexisting attractor prediction and multi-parameter. So this is a very simple example of single pendulum reservoir. We have considered the forced pendulum, where F is the amplitude of the forcing and there is the periodic forcing from the both side, and this is the absence of the forcing dynamics, and with the quasi there's a forcing dynamics is the quasi periodic in nature. Okay, so I'll just tell you the bifurcation diagram. Bifurcation diagram is the state of the system as a function of parameter, how it changes. Okay, so I have plotted this. The top panel shows the asymptotic and transient dynamics as a function of the amplitude of the forcing. So transient is you start from the very beginning and don't remove the initial period. So you can see that it has a more rich dynamical behavior as compared to the asymptotic. Similarly, if you look at the frequency of the external forcing with the asymptotic and transient dynamics, you can see that there is a difference. So what is our objective here? What we want to do is, our objective is to use the pendulum as a reservoir, single node reservoir instead of network, and we want to give some input. What we want to give is a like Lorentz is a like climate model which was proposed in 1960s, and if I give the x state variable dynamics, can I predict the y and z variable dynamics with this setup? Okay, so this is my objective. So what I will do is now input of the dynamical system, which is my Lorentz system, I have to encode into the reservoir. So the information of the Lorentz, where to put. So I have many choices. What choices I have? I can store into the state of the pendulum x. I can store into the velocity component of the pendulum. I can also store into the amplitude of the external forces or frequency of the external force. So what I will do is, I will use the two choices of amplitude and frequency encoding, and I will, the input is the dynamical system input which I want to predict, u, which I scale to the range of the frequency or the amplitude, so that there is a proper mapping to that. Okay, and then the input information is recorded on the state of the dynamical system, and that you can see that the equation is this. So if F is replaced by F plus U, okay, and once F is replaced by F plus U, the state of the dynamical system is carrying the information of U, which is the input. Now, after every iteration, I reset the reservoir initial condition to 0, 0. So that we are doing that, we want to train, so that we want to fix it to again through the same state. Now what we do is, and we record the transient dynamics because that is more rich, and we record the state of the reservoir at the particular sampling with the particular sampling rate. So state of the reservoir can be like storing this x at a particular time interval. So I will get this the state of this length kappa and tau. Tau is 2 pi over kappa sigma. And then what we have to do is, now we can have a two task. One is the dynamical system, which is the temporal task, which is evolving in time, or you can also try to fit the polynomial, which is a non-temporal task. Okay, so for the non-temporal task, you just take this S matrix, and for temporal task, what you do is, because you need to have the time evolution of the dynamical system, so you go into the previous input states with the some weights which is uniformly distributed between 0 and 1. So you have a weighted collection of the previous state. So you record the sum of the previous state, which is giving you the history of the state of the system. Because you are using only one node, so you need more number of states, and which you are creating in the temporal space, not in the spatial state space. Okay. Now you give the input to the reservoir and output is your state, reservoir state S, and non-temporal task can be simply the state at a given time, and for temporal task you take the weighted collection of the last m states. Okay, so your reservoir now is built, which is this matrix. Now you can see that the output V is W times R. R is already known from the system. V is during the training time is given to you. So you can find out the W from Morse-Penrose pseudo-inverse method. Okay. Now you can approximate the like any polynomial. You can see that this is a good fit with the root mean square error, which is of the order of 10 to the minus 8 to 10. You can also do this input to the x variable of the Lorentz and predict the y and z variables. And this prediction is quite well with the RMSE of 10 to the minus 3 in the both cases of amplitude and frequency encoding.
Your
Yes.
Y vector is some sampling of Y and Z. Your capital.
This.
The number, huh?
Yeah.
So your X vector is the X input of Lorentz.
X vector is this X vector is the state of the reservoir.
So U vector is the X of Lorentz.
Correct.
And Y is Y or Z of Lorentz.
Y is
For the training
Huh.
part, right? Training.
When you're training
You're
it.
training it.
yes,
One will be the target variable, right?
yes,
Y or Z of.
So it
Yes.
is a Y or Z.
yes.
You'll have different W outs, right? You'll have different W out, one W out for Y prediction, one W out for Z prediction.
Yes, correct. Yeah. So now you can see that if you look at this equation, this is the state of the reservoir. U is the input, which is your dynamical system, which you really want to predict, and this is Y is the output state of that reservoir. And these two equations are connected. So tomorrow I will tell you more about we'll do the dynamical analysis of the state of the reservoir, because you have an input as a dynamical system, the reservoir is another dynamical system, and these two dynamical systems are talking to each other, and then you are predicting the state of the input dynamical system from this dynamical system, because this dynamical system is carrying the information of the input dynamical system, and because of their interaction, which you can think of like one dynamical system is interacting with another dynamical system. So when they start evolving together, then the prediction will be good. Is a kind of synchronization of the input dynamical, the target dynamical system with the reservoir as a dynamical system. You can also use the Duffing oscillator as a reservoir. Okay, I will not go into the detail, but tomorrow I will use the Duffing oscillator as an input and use the network reservoir to understand or predict the dynamics of the Duffing oscillator, which is has a large number of applications in very different areas, especially in the engineering systems, mechanical systems and all. So I will conclude here that the theory of dynamical system address complex behavior of many natural systems, as we have seen that they show the variety of dynamical behavior in terms of variety of attractors. There can be a coexisting attractors, there can be a phase transition or bifurcation from one state to the another state. And reservoir computing is an approach to make the machine learning algorithm much faster with the dynamical system as a reservoir, as we can replace the hidden layer by the dynamical system and optimize only the readout part, which is the W out weights at the output layer. And single node reservoir, which I have mentioned, that the single pendulum or single Duffing oscillator or single neuron model network, or it is the electronic circuit, RC circuit can also work, or a delay system can also work. In the delay system, single node will give you basically the infinite dimensional system because of the delay. And then tomorrow, as I said, that we will move to the prediction of the coexisting attractors and multi-parameter dynamics. So with this, I thank you all and open for questions. Yeah. Yes. Yes.
In the reverse order, like the direction, I know my principles, I can fix waves and then I can, if I can put the or like I could understand that it is in this direction. We could do the physical. Did I
there.
get the sense of?
I'm not clear, but what I'm understanding is, so there are two different aspects of this reservoir computing is dynamical system as a reservoir. So you don't care what is to be predicted. So you are trying to understand the dynamics of the reservoir, okay, which is a single node reservoir or network of reservoir. So you try to understand, you try to replace the one reservoir to another reservoir or another reservoir and try to understand the dynamics of this reservoir, which reservoir will work better, or what is the optimal node of the reservoir size, whether the static network will work better or dynamic network will better. That is one aspect. Another is you fix your reservoir by equistate network, which is a random network. Okay, it is in the complete mathematical framework a random network like this, and then you try to take different examples. You try to, so this is your standard framework, and now you replace U by different input as a dynamical system, and you see that this reservoir can predict the one dynamical system or another dynamic. So predicting dynamical system with reservoir or reservoir as a dynamical system, these are the two different directions of study.
Tomorrow there's another talk to get discussed. So let me call this and Nag, right? The national